In this video, we're going to look at what we mean by center of mass. Let's suppose that we have several particles of masses m1, m2, and mn at points on the x-axis x1, x2, up to xn. Then we say that the center of mass is at x bar, which is sigma mi xi divided by sigma mi. Let's have a look and see what this means. Firstly, let's suppose that we have equal masses at x equals 3 and x equals 9. Two masses both equal to m. If we join these two with a light rod, then we would have something like that. And if we looked for the balance point of this system, we would expect the balance point to be right in the middle at x equals 6. Okay, let's see what happens if we use this formula. First of all, we need to work out what is sigma mi xi. That is the first mass, which we'll take as the one at 3m times 3, plus the second mass, m times its x-coordinate, 9. That gives us 12m. Sigma mi is just add up the masses, m plus m, that is equal to 2m. Then x bar is sigma mi, let's see if we can write that properly, mi xi divided by sigma mi, that is 12m divided by 2m, that is 6, which is what we expected. And so we say that x bar equals 6 is the center of mass. Suppose now that we have two unequal masses. Let's suppose that we have a mass of 2m at x equals 3 and a mass of m at x equals 9. What do we mean now by the balance point? If we tried to balance by the middle point, and I think you can see that the 2m would fall down and that the m would go up. So our balance point has got to be somewhere back this way. Let's look at the formula x bar equals sigma mi xi over sigma mi. In this case, mi xi, the first mass is 2m times 3. The second mass plus is m times 9. And we want to divide that by the sum of the masses, which is 2m plus m. That equals 6m plus 9m is 15m, divided by 2m plus m is 3m, and that is 5. So this is suggesting that the balance point should be at 5. Does this make sense? Let's just move that down a little bit, get it out of the way. Well, if the balance point is at 5, what happens if we decide to take moments about the pivot? Then we would have here a force downwards of 2mg. We would have here a force downwards of mg. And if we look at the anti-clockwise moments about the pivot, we would have force times distance, 2mg times 2, distance from 3 to 5. If we look at the clockwise moments, then we would have mg times the distance from 5 to 9 is 4. Well, we can see that the anti-clockwise one is 4 mg, the clockwise one is 4 mg, and therefore that the system balances about the point where x is 5. And so again, we say that x bar equals 5 is the center of mass. What happens if we're a little bit more ambitious? Let's suppose we have three masses. A mass 3m at 3, a mass 2m at 6, and a mass m at 9. I think we can see that the balance point can't be at 6. It must be, because of the 3m, it must be somewhere down here. Well, let's try and sort out where. Let's suppose that we use the formula again. X bar is equal to sigma mi xi divided by sigma mi. This will be 3m times 3 plus 2m times 6 plus 1m times 9, all divided by 3m plus 2m plus m. Well, on the top we get 9m plus 9m is 18m plus 12m is 30m. If we divide that by 3m plus 2m plus m, that is 6m, and we get that this is equal to 5. So this suggests that the balance point should be at x equals 5. Does this work? Well, let's take moments about the pivot again. If we take 3mg, 2mg, mg, forces acting downwards, then my anti-clockwise moment is going to be 3mg times 2, which is 6mg. My clockwise moment is going to be 2mg times 1 plus mg times distance from 5 to 9 is times 4, which is 6mg. And so the moments balance out, and it's sensible to say that the system would balance about the point where x bar is 5, and we say that x bar equals 5 is the center of mass of these three masses, 3m, 2m, and m. We can generalize this, and if we have for m n masses or n particles of mass m1, m2 up to mn at points x1, x2 up to xn, the center of mass is at x bar equals sigma mi xi over sigma mi. You will find this in your textbook, M2 on pages 31 to 34.